total internal reflection, application of total internal reflection, and dispersion of light. Refraction of light. The following subtopics will be covered: refraction of light, critical angle, total internal reflection, application of total internal reflection, and dispersion of light.
Introduction. When you put a cooking stick in water, it appears bent. A swimming pool appears shallower than it actually is when viewed by an observer from above. When there is a drizzle and the sun shines at the same time, the rainbow appears. There are some of the phenomena that do occur due to refraction of light when it passes through different media. Click the play button to see some of these phenomena. Refraction. The animation below shows a ray of light crossing on air glass interface, that is, boundary. Play the animation below and observe what happens to the ray before and after crossing the boundary. Discussion. When a ray of light travels from a less optically dense medium to a more optically dense medium, it bends towards the normal due to change in the speed of light across the boundary. This bending of light is referred to as refraction. Snell's law states that sin I divided by sin R is equal to a constant for all angles of incidence and their corresponding angle of refraction for a given pair of media. Therefore, the ratio of the sine of angle of incidence, I, to the sine of the angle of refraction, R, is known as the refractive index. Critical angle. When light travels from an optically denser medium to an optically less dense medium, it is refracted away from the normal. The animation below shows what happens when the angle of incidence is varied. Play the animation by increasing the angle of incidence until the angle of refraction is 90 degrees. Observation. When the angle of incidence was increased to 42 degrees, the ray was refracted with an angle of refraction equal to 90 degrees. Discussion. If we apply the Snell's law, in this case, we have refractive index of glass when the ray travels from glass to air is equal to sin C divided by sin 90 degrees, which is equal to sin C divided by 1. Refractive index of glass when the ray travels from glass to air is equal to sin C. Let this be equation 1. From the principle of reversibility of light, refractive index of glass when the ray travels from air to glass is equal to sin 90 degrees divided by sin C. Refractive index of glass when the ray travels from air to glass is equal to 1 divided by sin C. Let this be equation 2. From 1 and 2, we have refractive index of glass when the ray travels from glass to air is equal to 1 divided by refractive index of glass when the ray travels from air to glass. Conclusion. Critical angle is the angle of incidence in the optically denser medium whose angle of refraction is 90 degrees. It is denoted by C. Total internal reflection. A ray of light traveling from a medium of higher refractive index to one of lower refractive index will not undergo refraction at every angle of incidence. The animation below shows what takes place when the angle of incidence is 1. Equal to the critical angle and 2. Greater than the critical angle. Play the animation to observe the ray's behavior in both cases.
We learned that when the angle of incidence, I, is equal to the critical angle, C, of glass air boundary, the refracted ray moves along the boundary. When the critical angle C is exceeded, there will be no refraction, but the ray will be totally internally reflected. Application of total internal reflection. The following are some of the applications of total internal reflection. Prism periscope. Periscopes are used to see over the top of an obstacle. A prism periscope consists of two right-angle isosceles prisms. It produces a virtual upright image. Play the animation below to see how this device works. Optical fiber. This is a flexible, transparent cable used to transmit light energy carrying signals such as images or messages. Inside the cable, loss of light energy is prevented by multiple total internal reflections. Play the animation below to see how reflection occurs. Note that other than communication systems, optical fibers are also used in medicine to view internal organs of the body. Dispersion of light. Play the animation below to observe how light is dispersed.